Okay, first of all, I would like to thank the organizers for inviting me to give this presentation and to conclude that session. And so it's not going to be about mineral physics so much, but more about the application of mineral physics results, and in particular, those regarding thermal conductivity applications to the thermal evolution of the Earth's core. So, the questions I will address are mostly of two sorts. One is what are the requirements for running the geodynamo? And we know there was a magnetic field for at least 3.5 billion years. So we know that these requirements must be met. And this question has two parts. One is about what is the requirement, what are the requirements now, and what were the requirements before the inner core started to crystallize. And the second set of questions is what are the implications of these requirements for the thermal evolution of the Earth's core, and in terms of evolution of the CMB heat flow, age of the inner core, and evolution of the temperature at the CMB. Oops. All that is based on two equations. The first one being the energy balance of the core, where the total heat loss, CMB heat flow, is balanced by four terms, if you think there is radiogenic heating. And so that's one term. The other three terms are circular cooling, latent heat, and compositional energy due to redistribution of light elements in the core when inner core is crystallizing and releasing light elements at the ICB. All these three terms here can be written as functions of the inner core radius times its growth rate with time. And so when you write this equation, you can see that if you know the heat flow at the CMB as function of time, you can actually compute the growth rate, the growth history of the inner core, meaning that since we know the present size of the inner core, we can actually compute that to the time all the way down to the moment it started to crystallize. So we can actually compute the age of the inner core. That's for the recent period, and of course before that there is no inner core by definition. And before that, the equation, the energy balance is simpler. There is only circular cooling and possibly radiogenic heating, and then it is parameterized by the temperature at the center or the temperature at the CMB, whatever. That's for the first equation. The second equation is an entropy balance, which can be combined to the previous equation, to get an efficiency equation where on the left-hand side we have all the dissipation terms, and these are maintained by the same four terms times some efficiency factors, which are different for each term. On the left-hand side, the important thing is that there are three sorts of dissipation. There are two most important ones, of course, are the mechanical and magnetic, ohmic dissipation, which, viscous and ohmic dissipation are all in these terms here, and these are the useful dissipation. These are related to convection and dynamo maintenance of the dynamo. But in addition to that, there is an important dissipation term, which is due to the conduction along the isentropic temperature gradient in the core. And this is proportional to the thermal conductivity of core material. And it happens to be a quite large number, as we will see just after. So we can, so that's an important first point. And so another point to make here is that compositional energy has a higher efficiency factor than the thermal energies. So using these two equations, we can, for a given dissipation, compute what is the growth rate of the inner core that is needed to maintain that dissipation, which can be plugged back into the energy balance to get all the energy terms. Oops. Oh yeah. Before that, let's discuss a bit about the thermal conductivity. That's where everything is new. All I showed before is actually, is a theory that has been developed for quite some time now. But this old game has to comply with a new rule now, which is coming from the fact that the thermal conductivity has changed quite a bit in the last couple years since the publication of three different papers that have that are independent and give essentially the same answer on the thermal conductivity, which is about 3 times larger than the conductivity value that most people were using before. And knowing the conductivity in the core, which depends on depth and also on time because of the thermal evolution, you can compute the heat flow, the heat flux along the isentropic temperature gradient, which when you multiply by the surface at the CMB, gives you a total heat loss, total heat flow along the isentropic gradient, which is 13 terawatt, and it's quite a large number. So now, for any given value of the ohmic dissipation between, or the total dissipation between, say, 0 and 3 terawatt, you can compute what is necessary as Ecole growth rate to maintain that dissipation. And so that's this number here, and this is the one without radioactivity. If you take a 0 dissipation, which you will agree with me is a minimum bound, we don't know how good that minimum bound is, but it's clearly it cannot be less than 0. Already, that gives you Ecole age, which is 1400 million years, 1.4 billion years. Okay, and that's therefore a maximum age. If you add, say, 200 ppm of potassium, which is probably a higher bound, that increases that age, but not by a large amount. In fact, it's not a very good way of maintaining the dynamo. So that's for the present time, and if you go back to the time before the Ecole started to crystallize, instead of, I mean, you can do the same kind of exercise, but predict what is the necessary cooling rate of the core to maintain the same dissipation. And here again, if you take the minimum value, that would be 0, you get 400 Kelvin per gigayear, which is quite a large amount of cooling. So, to answer the first set of questions, the age of the Ecole must be less than 1.5 gigayear, and the cooling rate must have been more than about, say, 1200 in 3 gigayear. Then we can compute, again, for the same range of dissipation, we can compute the contributions to the energy and efficiency equation, and that's for the present time here. The reason why I wanted to show that is because you can see that the 0 dissipation is obtained for heat flow at the CMB, which is about 7 terawatt. And it's considerably lower than what is transported along the isentropic gradient at the top of the core. And this is possible because at the present time, we have compositional convection, which, although it's a small player in the energy balance, has a much higher efficiency in converting into dissipation than the other terms, and because of that, it can act against thermal stratification. So it's possible, at least from a thermodynamic point of view, to run a dynamo with a heat flow at the CMB, which is much lower than the isentropic heat flow at the CMB. Okay. But that's for the present time. Of course, this possibility does not exist for the early time before the Ecole started to crystallize. And in fact, what I find is that in order to maintain a 0 dissipation, the heat flow must be 15% higher than what is transported by conduction along the isentropic temperature gradient. It means that the heat flow must be more than 16 terawatt in that case. So we can then compute the age of the Ecole for different values of the CMB heat flow now. And in this first calculation, I assume the heat flow at the CMB to be a constant ratio to the heat flow along the isentropic gradient, the isentropic CMB heat flow. So all this dashed line here is for sub-isentropic CMB heat flow, which is again possible for the time when there is an Ecole. But of course, it is not possible to have that before the Ecole. So this means that for this to work, and we know that these ages are much lower than the age of the magnetic field, it means that for this to work, we need to have a jump of heat flow across the CMB when the Ecole started to crystallize, which is quite unrealistic because the mantle doesn't care so much about the fact that there is or is not an Ecole. Okay? So a more realistic bound is obtained by saying, well, let's try to find a minimum value of CMB heat flow which evolves with time and just becomes sub-isentropic at the time of the Ecole crystallization. And that will actually give a much lower heat flow at a much lower Ecole age, and the maximum is obtained here for the minimum value to maintain a positive dissipation, and it's 900 million years. But again, this is also a bit unrealistic in the sense that it would be a surprise that the heat flow at the CMB becomes sub-isentropic just at the time the core started to crystallize. Okay? So in fact, a more reasonable assumption is to say, for example, that we keep heat flow at the CMB a constant ratio to the isentropic heat flow, but a value that is actually larger than the necessary, the minimum to maintain the dynamo before the core. So this is the type of calculation that is shown here. The important point here is to see that, so this is a calculation where the heat flow at the CMB is always 15% above what is the, above the isentropic heat flow, which is, as you can see, just barely enough to maintain a positive dissipation before the inner core started to crystallize. Okay. And from that, it's possible to compute the evolution of the CMB temperature, and this is the result I get from that. Starting from the present time value of about 4,000, we get a very large amount of cooling. And when you compare that to the range of melting temperature the melting temperature of mantle minerals at the CMB, you see that even though we may not have melt at the present time at the bottom of the mantle to explain ULVZs, as some people have proposed, when you go back in time, it's unavoidable to have melting of these minerals. And so that's actually the argument that is at the base of our proposal of this magma ocean at the bottom of the mantle for most of the history of the Earth. So it seems that I've been much faster than I expected. So to conclude, and I will just give you, so to conclude, so it is possible to compute the thermal evolution of the Earth's core with the minimal requirement to maintain a dynamo. One caveat here is that it is a standard model for maintaining the dynamo, that is thermal compositional convection in the Earth's core, using, for the present time, for example, compositional energy from inner core growth. This afternoon there will be a presentation in the session, the core session, where an alternative scenario is exsolution, and maybe that's another way of going against that issue. But if you accept the standard model of maintaining the dynamo, the heat flow at the CMB must be more than 15 terawatt for the last 3.5 gigayear. It means it is an important contribution to the thermal evolution of the Earth as a whole. Okay, you have to take that into account when dealing with the thermal evolution of the Earth. I mean, it's a large number. Okay, it's a third of what comes out of the surface of the Earth. The age of the inner core from these calculations is less than 900 million years, and probably much less than that, in fact. Again, this is a minimum CMB heat flow. And the CMB temperature has decreased a lot. And here I say 1,000, but in fact, the plot I showed was much larger than that. The reason why I'm stating a smaller number here is because I haven't showed you the effect of radioactivity. And of course, if you add a large amount of radioactivity, of a much larger amount than what I showed you before, you could decrease that, the number I obtained. So maybe 1,000 is possible. Okay, the result I showed you was more than 1,000. Okay, and again, there will be a talk this afternoon by Nomura et al. About the effect, the possibility of having potassium and thorium in the core, which could help to decrease the amount of cooling that is necessary to maintain the dynamo. And anyway, even that is already enough to justify the existence of a basal magma ocean for most of Earth's history. And that'd be all.
Thank you. Question? Yes.
Nice analysis. Lurking behind this is the unsolved problem of the Uri number. The fact that Earth's heat flow right now appears to be half or more just due to cooling. Do you have an opinion about how that works as you go back in time? Because that seems to be a crucial part of understanding this.
Yeah, I agree. I mean, it's very important. In fact, if you take that, you can make a modified Uri number for the mantle, where in addition to radiogenic heating, you add this core cooling term as a source for the mantle. In that case, you get a Uri number which is about 0.7, which is something that could help to solve the thermal catastrophe of the, that is standard in classical thermal evolution models for the mantle. That means it's a way to avoid having too much cooling of the mantle. Okay, so in fact, I've done some of these calculations with including this type of heat flow. But then, of course, you have to factor in the melting, the freezing of the basal magma ocean, and there are many things we don't really know what is the effect of having this basal magma ocean on mantle convection itself. We don't yet have the scaling laws for that, in fact. So that's work in progress. But indeed, I think that's a good way to solve that very long-standing problem of the thermal evolution of the Earth. That's why I wanted to make this point. Yeah, we've made some calculations of that, and it could have started like 1,000 kilometers thick. We don't really know. Okay, there's too many unknown parameters to actually say give a serious number, but it's possible to have 1,000 kilometers thick. The important thing is that it takes very long time to cool down and to fully crystallize because of the effect, because of two effects, because of the effect of iron concentration by fractional crystallization and the effect it has on the liquidus, plus the effect that you have the core that is below that and is a very big heat reservoir. So all that this analysis was in the previous, the paper we published in 2007.